All right, excellent. All 5 judges have completed that process. So moving on, we are going to hear from, on the title, Shattering Records, How New Efforts Are Shaping the Future of Mid-Infrared Lasers. Joining us from the Department of Physics, competitor number 3, Jeremy Massengale.
Over the course of the last century, the rapid pace of technological advancement has fundamentally altered and forever shaped the course of our lives. The laser is one of these transformative technologies and is used for everything from the ordinary to the extraordinary. The interband cascade laser, or ICL, is unique among its various counterparts in that it is a low power consumption device, making it quite handy for any sort of portable or remote application. The ICL targets that part of the spectrum just beyond what the eye can see, the infrared. This type of laser takes advantage of the cascade process to enhance its efficiency. Now, you can think of the cascade process like a ball rolling down a set of stairs, where the ball represents an electron that is traveling through the ICL. With each step the ball bounces off of, a new particle of light is created. Now, there are many practical applications for the ICL, but perhaps chief among them is in the sensing of various gas and chemical species, some of which can be biological signatures of life. In fact, an ICL is on Mars at this very moment and was used only a few years ago to detect the changes in the methane concentration in the atmosphere. My work here at OU has focused on a new class of ICL that are better suited to long wavelength operation. Here, we use a feedback process to inform our research goals, beginning first with the device design. We then employ a crystal growth technique to build that structure in real life. That grown wafer then goes through a fabrication process where it is transformed into a practical device, small enough to sit on the tip of your finger, which we can then hook up and test. Now, there are 2 key problems that arise at longer wavelengths. The first is the increased heating within the device, which can be a real killer for its performance. And the second is the reduced light generation rate. To solve the problem of heating in the ICL, we have redesigned that part of its structure, which is responsible for confining and guiding the light. And this has resulted in ICLs with 15 times more output power than previously tested devices. To address the problem of reduced light generation, we have also redesigned the part of the ICL which is responsible for generating the light. And this has led to the longest operating wavelength ever observed in an ICL, nearly 20% longer than the previous record holder. These accomplishments by my group here at OU have helped to pave the way to a better fundamental understanding of this new type of technology. We have extended this device's practical application range, serving endeavors such as the sensing of various gases and chemicals, whose signatures exist at these longer wavelengths. It will be exciting to see what the future holds for infrared laser technology and what new discoveries are yet to be made. Thank you.